Today we're going to talk about the reference tables that will help you with organic chemistry. So I want to show those to you separate from the regular lectures, and you may or may not need this set. But in organic chemistry, there's going to be three reference tables that are going to be super helpful to you. Reference table P, Q, and R. So as you watch this, you're probably going to want your reference tables out. Reference table P lists the prefixes that we will use. Now, these are not the only prefixes that are used in organic chemistry. These are the ones that the state will use for you, so you're not going to have organic molecules that have more than the 10 carbons in them. There are, just understand, other prefixes besides these. So this is how we're going to count in organic chemistry, and this is for carbons. Okay, these prefixes are for numbers of carbons only. When we're talking about other things, if you have two chlorines, we usually say dichloro. So other prefixes for things other than carbon, things like di meaning two, mono is one, tri is three, tetra, we've used carbon tetrachloride before, that's four. So these are prefixes that you're used to, and these are going to be for other things like chlorines and fluorines, numbers of branches. So we'll still use these prefixes. But when we're talking about carbons, these are the ones we use. Meth, eth, prop, but, pen, hex, hep, doc, non, dec. And I can say them really quickly like that, and I'm not reading because I've memorized these. Meth, eth, prop, but, pen, hex, hep, doc, non, dec, because these are very, very common for us to use. The quicker you learn these prefixes, the easier naming some of these organic compounds are going to be. So when you go to get new fuel for your grill and it's propane, that tells me that there's 3 carbons in that molecule. The octane rating on gasoline tells me that there are 8 carbons in that molecule. On to table Q. On table Q, we have hydrocarbons. So again, these are not the only hydrocarbons that exist in organic chemistry. These are just 3 of the classes of hydrocarbons that the state is going to test you on. Hydro, standing for hydrogen, and carbon, standing for, of course, carbon. So these are molecules made of only carbons and hydrogens. That's all that's in them. There's only 3 that you need to know: alkanes, alkenes, and alkynes. Their endings will tell you how their structures look. So all of the alkanes end in ane: methane, ethane, propane, butane, etc. All the alkenes end in ene: ethene, propene, butene, pentene. And all the alkynes end in yne: ethyne, propyne, butyne, pentyne. The general formula is going to help you figure out what numbers to use, and the N is the number of carbons. So if I am back talking about my gasoline and I see that there's an octane rating, reference table P told me that oct was 8 carbons. That's going to be my N. The general formula for something that ends in ane is CnH2n plus 2. So Cn, the N is 8, H2n plus 2, so I have 2 times 8 plus 2, so 16 plus 2 is 18. And that would be your formula for octane. So you can very quickly figure out the formula for any of the 3 hydrocarbons that we're responsible for. So for example, if we said we had pentyne, we'll do one more quick example here. Pent, according to reference table P, means 5 carbons. The yne ending tells me that I have an alkyne, and I'm going to use the general formula CnH2n minus 2. So Cn, the N is 5, H2n minus 2, so that's 2 times 5 minus 2, so 10 minus 2 is 8. And there's the formula for pentyne. So any of the 3 hydrocarbons that they give you, you can figure out what their formulas are based on their name. They're also showing you their structures, and the reason they're showing you the structures is so that you know what's special or different about them. The alkanes with the A and E have all single bonds between their carbons. Now they're talking about the bonds between carbons. So no matter how many carbons I have, if I have the octane, all 8, 1, 2, 3, 4, 5, 6, 7, 8 carbons will have single bonds between them, and then we put the 18 hydrogens all around. One of the things you're going to see is that a lot of times we don't bother to write the H's because it gets messy. You need at least the lines, though. You either have to write the H's or at least put the lines around the carbons. Alkenes with the E&E ending have one double bond between carbons. Okay, so they're talking about this bond right here. If I have, for example, instead of ethene, if I have propene, prop meaning 3 carbons, I would have one double bond and the rest are single bonds. And then we put hydrogens on. Now you notice there's fewer hydrogens on these carbons when you look at the example. The alkanes had 1, 2, 3 hydrogens. The alkenes only have 2 hydrogens. That's because each carbon can only have 4 bonds. So this carbon has 1, 2, 3, 4 bonds. This carbon has 1, 2, 3 already. He gets 1 hydrogen. And this carbon has 1 bond already. 1, 2, 3 hydrogens. So it's going to be tricky around where the double bond is. You're going to have to be careful and count when you're putting on your hydrogens. The alkynes, you've probably figured out the pattern already, have 1 triple bond and just 1. So it doesn't matter how many carbons you have, only 1 of the bonds is triple. So if we use our pentyne example, 1, 1, 2, 3, 2 carbons, 3, 4, 5. And again, we're going to count how many bonds are on the carbons. 1, 2, 3, so he gets 1. 1, 2, 3, 4, he doesn't get any hydrogens at all. This guy has 2, so he gets 2, 2, and this last guy gets 3. That's our 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. You should always go back when you have to draw a structure, count the numbers of carbons, count the number of hydrogens, make sure they match your formula. One of the things that you should most definitely do on this table is mark which ones are saturated and unsaturated. We'll talk about that specifically in a lecture, but your alkanes are your saturated hydrocarbons, and the alkenes and the alkynes are unsaturated. What that means is they hold the most hydrogens as they could. If I took this propene and I broke this bond, I could add an extra hydrogen to that molecule, so that makes this unsaturated because it could hold more hydrogens. On this guy, there's no way to add more hydrogens because they're all single bonds. So mark that on this reference table. On to reference table R. Not every organic molecule is going to have just hydrogens and carbons in it. Most of the time, they're going to have other things attached to them. So I know I zoomed this out so it's smaller. I want to show you the whole table at once first, and we'll zoom in later if we have to. There are other things attached to it. So this first group here is the names of the types of molecules when you have other things attached. Okay, and then this functional group are the other things. What besides hydrogen and carbon are in my molecule? So if you're trying to figure out what kind of organic molecule you have, the first thing you do is look at what's in it. If it's only carbons and hydrogens, then you use table Q. It's one of the hydrocarbons. If there's anything else, we are going to use table R. So there's a few things that are really easy that only show up in one class. So if you have a halogen, so we're still working with some of you remembering which ones are the halogens. The halogens are things in group 17. So fluorine, chlorine, bromine, and iodine, then that's right here. It's a halide. So that's really quick. That's the first thing I would look for. Is it a halogen? Next, if you don't have a halogen, So that's the first thing you should look for. Then I would look for nitrogens, because there's only two groups way down here at the bottom that contain nitrogen. One of them are amines and one of them are amides. So if it does have a nitrogen, you're going to ask yourself, nitrogen only, then that's an amine. Or nitrogen and oxygen, that's going to be an amide. Okay, amines and amides. Okay, so that's next. If there's no nitrogen at all, you're going to then, of course, be on to oxygens, because if you look in the middle of the table, that's all that's left. There are two groups that have two oxygens. So you look at the number of oxygens. If there's two oxygens, then that's going to be either at the end, so it looks like this, double bonded OOH, and that's going to be an organic acid, or are my oxygens in the middle, and that's going to look like this, double bonded OO, and then there's another carbon on it, that's going to be an ester. Okay, so you're going to split those here. Notice, even if you have a hard time figuring out whether it's at the end or in the middle, you've at least narrowed your choices down to a 50-50 guess by noticing that there are two oxygens in your compound. Okay, these guys all have one oxygen. There's 4 of them left. So if we only have one oxygen, you're going to look to see, is it held on with a double bond or only single bonds? So if there's a double bond, we're right here in this section I'm boxing in pink. We're back to, is it the end or the middle? So if your double bond is at the end, so we have C double bond O with just an H, then that's going to be an aldehyde. And if it's in the middle, see the double bond O is off the top, and on either side you have carbons, and this is going to be the smallest one of these you can possibly make. This is called a ketone. And then what's left are those two last groups there, and I'll use orange for those. Alcohols and ethers is your, again, single bonded oxygen attached to a hydrogen for its other part. That's going to be an alcohol. So what you have is a hydroxyl group somewhere on your molecule. Or is it attached to carbons? So you have a carbon, an oxygen, and a carbon. It's holding 2 chains together. Then that's going to be an ether. Take your time and split your table up. When you look at a molecule, really kind of look at what it's made out of. Go through this list in order and see if you can figure out what you've got. All right, I'm going to take a break. I'm going to erase this. So if you need to write this down, pause it and write it down now. And then we're going to zoom in on this and draw a few examples so I can show you how the example will help you name yours. I'm only going to do a couple. So here I am, zoomed in a little bit more. And when you look at your reference table, they are showing you the functional group, so this is what makes it that special type of thing. This is where you're going to be looking for that 1 oxygen or 2 oxygen, single bonds, double bonds, etc. General formulas, the R's are going to be your chains of carbon, so this shows you where your carbon chains attach onto your molecules. And then we have our examples over here. Now what they're showing you here is a molecular formula, but this is what they call an expanded molecular formula. And at the top, I have the condensed molecular formula. So you can see where if it just says C3H7Cl, that's not as helpful for you to figure out what the structure looks like as if you have the expanded molecular formula. In the expanded molecular formula, Each of these carbons is a link in a chain, and you can just draw them exactly the way they are. So if I were to draw this 2-chloropropane, CH3 is my first link, so CH3. CHCl is my next link, so CHCl. And then CH3 is my last link. The carbons are each link in the chain. Whatever goes with that carbon, okay, so whatever's listed until you hit the next carbon is what goes on that carbon, and you just link them all together. If you don't give carbons enough bonds, then you just add extra bonds in to make it so that each carbon has 4. Look at the name, 2-chloropropane. So we already know that prop means there's 3 carbons, and there's 1, 2, 3 carbons in my chain. The ANE tells me all of the bonds between the carbons are single bonds. The 2 is telling me a location. Whenever you see an actual number, and not the prefix di, but the number 2, that tells you which carbon it is. And you always count so that you are using the lowest numbers possible. And the chloral is telling me what is on carbon number 2. So if you look at the structure, there's my 1, 2, 3 carbons, all single bonds. There's the chlorine on carbon number 2, and I just filled in hydrogens around. If we use that same pattern for this next example, so I drew another example over here. If I looked at this and I said, oh, fluorines, so this is a halide. So I'm going to draw, hex means 6 carbons, ANE, they're all single bonds, di is a prefix for 2, so I must have 2 fluorines, and those 2 fluorines, their locations are on carbons 2 and 3. So I start with my 6 carbons, 1, 2, 3, 4, 5, 6. On carbons 2 and 3, I have to put a fluorine. So carbon, whichever end you start counting from, you have to keep counting from that end. I can't count 2 from the left and then 3 from the right. That would mess up my molecule. So 2 from the left, and I put a fluorine, and 3 from the left, I put a fluorine. For our purposes, it doesn't matter if you put both of the fluorines on the same side or if you put them on opposite sides. When you take organic chem in college, it will make a huge difference. They'll tell you how to figure that out. For our purposes, we don't care. And then now I put the hydrogens all around so that each carbon has a total of 4 bonds. And there's my molecule. The names of organic molecules are basically instructions. The pattern over here will help you figure out what those instructions mean. So let's look at an ether. So I put an example of how I'm going to use this table to figure out the structure of a halide, an ether, a ketone, and an ester. So for the ether, I know it's an ether because it says ether in the name. So I look at my example. Here again, we have methyl ethyl ether. Look at their example. They have 1 carbon, the oxygen, so that's my functional group right here, and then 2 carbons. Meth means 1 carbon, so this first chain must be this first part. The YL ending means that it's a branch. So I have a branch made with 1 carbon. Ethyl means 2. The YL is the branch. I have a branch made of 2 carbons, and it's an ether, so my 2 branches are being held together by the oxygen, which is exactly what my general formula is telling me. So if I know I have an ether, I'm going to have an oxygen holding on to 2 branches. Ethyl tells me that my first branch is made of 2 carbons. Propyl tells me that my second branch is made of 3 carbons. And then you just have to put hydrogens around until every carbon only has 4 bonds. Remember that your oxygen can only have 2 bonds. Don't put any hydrogens on the oxygen. Nice and simple. This one ends in -one, so the -one ending is telling me that it's a ketone, because if we look at my example, that's what the name ends in. This one says pentanone. I know that pent means 5 carbons. If I look at my example, there are 1, 2, 3, 4, 5 carbons total, so I must just put my carbons in a straight line. The 2 is telling me a location. A location of what? Well, it's telling me the location of my functional group, which is a double bonded oxygen. So if I look again at my example, carbon 1, 2, that's carbon number 2, he has the double bonded oxygen. So I'm going to try the same thing over here. Hex means 6 carbons. 1, 2, 3, 4, 5, 6. The 3 is the location of my functional group, which happens to be a double bonded oxygen. So carbon 1, 2, 3 gets my double bonded oxygen. And then I just put hydrogens around so that each carbon gets 4 bonds. Be careful, the carbon that has the oxygen already has 4 bonds, so he doesn't get any hydrogens. So I can use their pattern to figure out my structural formula. And then last down here, the ester. Their ester says methyl. I know that this YL means a branch, so there must be a branch made of 1 carbon. Propanoate. The anoate ending is going to tell me that it's an ester. The prop means 3 carbons, so some part of this molecule has 3 carbons. 1, 2, 3 carbons, then my functional group, then my 1 carbon branch. So the branch is on the oxygen, and my 3 carbons go with the double bonded oxygen. So when I look at this example, butanoate, my 4 carbons must go with the double bonded oxygen. 1, 2, 3, 4. And because this is a branch, this must be the branch off of the oxygen, and prop means 3, so the branch off of the oxygen must have 3 carbons. And again, to finish this off, to make sure you get credit, add your hydrogen so every carbon has 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, already has 4. The oxygen only gets 2, so he's done. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then there's my propylbutanoate. We will specifically go over more examples of each class of compounds in the other lecture.